In this section of chapter 20, we'll talk about voltaic cell. A battery is a good example of a voltaic cell. And in batteries, it's the chemical reaction that provides electricity. Then we'll talk about EMF calculation or electromotive force, or simply we call it voltage calculation. So we'll talk about both voltaic cell as well as how we can calculate voltage of such a voltaic cell. In every voltaic cell, two reactions would happen simultaneously, which is one would be oxidation, the other reaction would be reduction. So in this example, you can see that zinc changes to zinc 2 plus, and copper 2 plus changes into copper. And obviously zinc is losing 2 electrons and copper is gaining 2 electrons. So this is what you're looking at, is the overall reaction in a voltaic cell. So electricity is due to flow of electrons, because when zinc loses 2 of its electrons, copper 2 plus receives those electrons, and that creates flow of electricity. Electricity is nothing but flow of electrons. So in order to understand how many moles of electrons are being transferred, we need to split this reaction into two half reactions. So I'm now splitting that into two half reactions. Zinc is forming zinc 2 plus and giving off 2 electrons per zinc atom. Or in terms of mole, 1 mole of zinc gives off 2 moles of electron and changes into zinc 2 plus. This reaction happens at anode. So normally we say that anode where oxidation takes place, because this is an oxidation reaction. Oxidation reaction means loss of electrons. Reaction where there is a loss of electron from the reactant. Copper 2 plus gains electron, becoming copper. So copper 2 plus receives electron. Receiving electron means reduction process, and it happens at cathode. So in a voltaic cell, always there'll be two ends. One would be anodic, the other one is the cathodic end or cathodic electrode. If you look at a voltaic cell like a battery, you'd see there's a negative sign and a positive sign. Anode would have a negative sign and cathode would have a positive sign in voltaic cell. So this is like a conventional thing. Anode where oxidation takes place, so scientists decided to assign a negative sign there. Cathode where reduction takes place, again scientists decided to assign positive charge when it's a voltaic cell. In electrolytic cell, what we're going to discuss toward the end of this chapter, in electrolytic cell, sign convention is just the opposite. Now to remind you, I have drawn these two for you. Cat red, cathode reduction. That means reduction takes place at the cathode. So make sure you remember this. Anox, anode oxidation. That means oxidation takes place at anode, reduction takes place at cathode in a voltaic cell, or the cell where you can spontaneously get electricity. Now here we're showing you one voltaic cell. Anyone can make this in the lab. Here you have, we're going to show you three things: anode, cathode, salt bridge, and we're going to explain why we need salt bridge. Again, in this case, zinc becoming zinc 2 plus, copper 2 plus is receiving electrons, becoming copper. So you can see that zinc is on the left hand side. That forms the 1/2 of the cell. Cell means you can consider cell to be the device by which you can get electricity. So half cell reaction will be given by zinc becoming zinc 2 plus 2 electron. Other half still will be given by the other half of this, copper 2 plus, receiving electrons becoming copper. Now, if you look at more closely, you see that metal is the zinc on the left-hand side. So this is zinc. You can see zinc. And when zinc goes into solution as zinc 2 plus, it gives off 2 moles of electrons. So in other words, picture you see 1 mole. I can show you another one. So it goes through the circuit and goes to the other end, where the solution has copper 2 plus. You can get copper 2 plus in the solution by adding copper nitrate in solution. So copper 2 plus receives electron and becoming copper, and it gets deposited. Since you have copper, that's metal. So you have another metal electrode on the other end. So copper gets deposited to the metal. So basically, as you pass electricity, as you get electricity out of this, you're going to get copper deposited on the copper end, and zinc gets used up as zinc 2 plus. Now there is a Saul bridge in between. Saul bridge is nothing but it maintains charges. For example, when zinc becomes zinc 2 plus, you get some extra positive charge. So Saul bridge supplies negative ion like NO3 minus to this side of the solution. Similarly, when copper 2 plus receives electron, there'd be loss of positive charge. So that means some positive charge has to come from the Saul bridge. So that's how neutrality is maintained, and you can get electricity out of this device. Now the question is, how do I calculate voltage? Idea is the following. Zinc losing electron by giving off 2 electrons, copper 2 plus receiving electrons. So you must have these 2 reactions going on simultaneously. It's like a football game where you have a quarterback. Of course, there are only 2 players in this kind of football game. Quarterback is throwing football, and receiver is going to receive electrons. And keep this in mind. If there is no receiver, quarterback in this case is not going to throw ball. So this is kind of a perfect game where there is no fumble. And so keep this in mind. You must have both receiver and the quarterback present in order for this transfer of football in this case. In case of electrochemical reaction, it would be the electron. So zinc is not going to throw electrons until and unless copper 2 plus is there, or something else is there, some other ion is there to receive those electrons. And that number has to be the same. That means if one half reaction gives off 2 electrons, the other half will have to receive those 2 electrons. Otherwise, there'll be no such transfer of electrons. So the question is, who is getting more credit here? If the quarterback is throwing ball and receiver is receiving the ball, and if everything is happening in a perfect manner, question is who gets more credit? Answer is both. Because if there is no quarterback, there'll be no ball thrown at the receiver. On the other hand, same could be said, if there is no receiver, quarterback cannot throw the football. Same would be the case in electrochemical reaction. Each half reaction is very important. So you have to add contribution of both in order to get cell voltage, or the voltage you can get by using a voltaic cell. So the left-hand side, this is the contribution coming from an anodic part or oxidation reaction, and the right hand side is a contribution coming from cathodic reaction or reduction reaction. And cell is usually represented by like this, the above cell, zinc followed by line. That line means zinc is separated by a zinc nitrate solution or any other zinc solution which gives zinc 2 plus. The double line stands for Saul bridge. On the other side, you have copper 2 plus that changes into copper. So copper 2 plus, and then again there is a line, means is separated, that solution is separated by a solid. The copper is solid. So this is how you can represent a cell or a voltaic cell. Always in this order. The one that gets oxidized on the left hand side, one that's reduced is on the right hand side. So you should be able to read it like this. Zinc is becoming zinc 2 plus, then Thal bridge, copper 2 plus is becoming copper. I already mentioned that unit of EMF is voltage or volt. Now volt times Coulomb gives joule, which is a unit for energy, unit for work. And keep in mind, Coulomb is nothing but the unit of charge. So if I know the charge that has passed through an electrical circuit with certain voltage, then just multiplying those two quantities, we can find out electrical work. In order to get EMF of the cell, you just need these two values. E0 oxidation, that's contribution coming from 1/2 cell where oxidation takes place. E0 reduction, E0 means the standard. These are all standard values. That means these experiments were done under standard condition. So E0 oxidation for zinc becoming zinc 2 plus is plus 0.76. If you look at the book, toward the end of the book, there is a table given. In that table, we'd find the value is minus 0.76. That's reduction potential. That means if zinc underwent reduction reaction, then it would have the value of minus 0.76. In order to convert that into oxidation, just change the sign. So minus 0.76 became plus 0.76 as we change from reduction value to oxidation value. The other half reaction would have reduction reaction, and so that you can use the number as it is. Then add these two numbers and you get the voltage of this particular cell or voltaic cell. So basically you need to have a half cell value which undergoes oxidation, the other half cell value which undergoes reduction process. Now, since we mentioned about reduction potential, what is the reduction potential? I need to better explain that to you. This is all based on this particular scale or assumption. You can say 2H plus 2 electron giving H2. We consider this to have zero value. That means H plus as the receiver of electron gets zero value, and everything else would be in comparison to this. So anything that is better receiver than H plus would get a positive number. If it is the worse receiver than H plus, would get negative numbers. So if you look at the table at page 841, you'll see those numbers, and I'm going to show you those that table too. This is the table I was referring to. If you look at the first number, 2.87, and if you look at the right hand side, these are all reduction reactions given. And this whole table is based on reduction reaction. And look at here, oxygen has zero, because that's the assumption that every number is in comparison with H plus electrode. So that means you have hydrogen electrode on one end, and the other half reaction would be made up of these, F2, 2E minus, giving 2F minus. And if you have a cell like that, you get 2.87 voltage. Similarly, for the second half reaction, if you couple that with H plus changing to H2, you get 1.51. So that's how scientists get all these numbers that you see in the table. If you go underneath H plus, you see these numbers are all negative. Why negative? They are worse receiver than H plus. These ones going upward from H plus, they're all positive because they're better receiver of electrons. So basically, by looking at this table, you find out which ones are better receiver of electrons. again, going back to the example of voltaic cell made up of zinc, and the other half cell this time is made up of hydrogen. I mean, that's how exactly scientists came up with that table and the values. So if I have a zinc and H plus or hydrogen electrode on the other end, hydrogen electrode is made up like this. If you focus on the right hand side, you allow hydrogen gas to pass through, and hydrogen covers this electrode on the right hand side where it's shown as positive, and so it acts as if the electrode, the whole metal, is made up of hydrogen, and it's in contact with H plus solution. H plus comes from any acidic solution. So basically, when zinc breaks down to zinc 2 plus, electron goes to the other end, and H plus receives those electrons, becoming H2. So that's how this whole reaction takes place, and the value of voltage is 0.76. And if you look at a half cell reaction, you'd see the value of 0.76 given. Now here we're going to show you better receiver and how is it going to affect overall EMF or voltage of a cell. Now I copied here two values from the back of the book. Reduction value for copper, which is 0.34 volt, and reduction value for zinc 2 plus is minus 0.76 volt. So these are all reduction values, assuming that they undergo reduction reaction. Now, keep this in mind. A better receiver would have a larger positive number. A worse receiver would get a larger negative number. But two of these half cells would make a cell, a complete cell. So keep that in mind. This is how we pick the best receiver. The best receiver is the one which has the largest value of reduction potential value. So between these two, obviously, the first one is the better receiver. It's 0.34, plus 0.34. The second one is minus 0.76. This is not as good as this one, the first one. So the better receiver is always going to receive electrons, and the other one has to reverse its role, and it would give off electrons. So in other words, if I'm going to combine this first reaction with the second one has to reverse its role. That means the second reaction has to go like this, zinc becoming zinc 2 plus 2 electron. So it will have to give up electrons, and copper then can absorb those electrons or receive those electrons. In question number 39, B as well as A, these are the two parts of this problem that I'm going to do. In part A, 39A, you're supposed to get the combination of half cell reactions that leads to the cell with largest positive self potential or EMF value. In other words, you need to combine two of these half cells. Remember, you need two half cells to get a cell or a battery. So the question is, what combination would give the largest possible EMF value? Obviously, it has to be the positive one. One quick way of knowing it would be, let's write down A. That's what we're going to do first. Before you go over A, let me show you. These are the reduction values I got from back of the book. Let's convert them to E0 of oxidation. The value would remain the same, but sign gets changed. So E0 reduction becomes E0 oxidation, and the value is, let's get these are all in voltage, minus 0.799. Just change the sign. Minus 0.34 plus 0.28 plus 0.74. So these are, let me double check. These are the oxidation relative. So these are the oxidation values, and make sure we have signs right. This will be just the opposite sign. Okay. Now, in order to do A, So they're asking for which combination would give the largest possible cell potential. I can quickly do it by getting the best receiver plus best, in my analogy I use the term quarterback. So best receiver and best quarterback would give you the best result. So best receiver, we determine it by the largest possible reduction value. So remember that best receiver would get the contribution of, in order to get cell voltage, E0 cell would be E0 reduction, that's coming from the best receiver, plus E0 oxidation coming from the best quarterback or best thrower of electrons, the one which throws electron or loses electron. How do I get those values? Let's look at that closely. The best receiver of electron must get the largest possible reduction value. The first column of number has the reduction values. So obviously 0.799 is the largest value, so that's the best receiver here. So let's write down that number, 0.799, obviously that's positive. And then best oxidation reaction, or the best quarterback, which most effectively loses electrons or readily loses electrons. Now we look at the second column, the largest value of oxidation, which is plus 0.74. So I'm going to write down that plus 0.74. And the sum of these two would give me the total cell voltage, which is 1.54. 54 volts. You could have done this same problem by just combining all possible, by taking into account all possible combinations. That means left hand side and right hand side, you add them and finally see. Of course, you cannot choose the same one twice. So if you choose this 799, then it'd be minus 0.34 or plus 2.28 or plus 74. That's how we find out what gives the best or largest voltage. In part B, the question is which combination in part B gives the smallest positive value of EMF or voltage. So let's try that. And keep in mind, you must have a positive number, cannot have a negative number. Because negative number means you're not going to get electricity spontaneously when you attach those two ends coming from anode and cathode. Okay, now in this case, again, you use primarily the combination 0.799 minus 0.34, 0.799 plus 0.28, 0.79 plus 0.74. So in that, just keeps on going and try all these combinations, and you're going to find that the smallest value you'd get for these combination, which I'm going to write down next, which should not take that long for you to find out, because you need to ignore, you cannot get any negative value. I'm talking about that when you sum these two numbers, anode and cathode value, and they will have to be positive, because that's what question is asking for, the smallest positive EMF. So minus 0.34, and that gives plus 0.459, and that's about plus 0.46 voltage. Here we're giving you examples of voltaic cell, flashlight battery. You know that there are different kinds of flashlight battery. AA, triple A, C, D, all these different types of battery. Car battery, which is also rechargeable battery. Alkaline battery, nickel cadmium rechargeable battery. Then fuel cell. By building those kind of cells, scientists are trying to get highly efficient electrical energy. So still a lot of research is going on in this area. So in this, the particular example that I am showing you here, the overall reaction gives you H2O2 combination giving H2O liquid. So end product is very simple, harmless, and quite useful.